All right. All right, so let me say that again. So we're going to be talking about hypothesis testing. This is going to be a continuation of a video that I pre-recorded last Wednesday. And now, most of the information that you need for this topic is in chapter 22. Now, there are other chapters that are mentioned in the syllabus. Those are chapters that were math department selected. However, I think with just chapter 22 and the and StatKey, I think will be sufficient for you to understand hypothesis testing. So you can read the other sections that are mentioned in the syllabus, but I know there's a couple sections in there which deals with contingency tables and how to do significance testing with that, which we will not cover in this course. That's actually an advanced topic. I'm not quite clear why that was even put into the syllabus. But the syllabus will not be covering that. We'll be dealing with just the simpler cases that we'll be talking about today and Wednesday. Now, the schedule basically is I'll be completing everything by Wednesday, all the topics in hypothesis testing. Again, Wednesday will be mostly problem solving. I'll show you exactly how to do a hypothesis test as far as your course is concerned. It's a very basic thing that we'll be doing, nothing complicated. And then next Monday, you'll have your final quiz, which would be quiz number 9, and it will cover hypothesis test. And I think it may cover a topic that in confidence intervals that we did not cover in quiz 8, which was the case of comparing two populations for proportions and means. But I'll talk more about that on Wednesday. Then, of course, we'll be reviewing for the third test. And the third test is next Wednesday, not this Wednesday, next Wednesday the 9th, because I think the semester ends that day. I believe the 10th is the reading day, and then final exams start on the 11th, Friday the 11th. Now, your class, I believe, I'll have to double check it, but I believe your final exam is on Monday, 2 weeks from today. So today is the 30th, so Monday the 14th, I believe, is your final exam. And I believe it's from 2:45 to 4:45, but you all received emails about it. I'll double check, but I believe that's the schedule for the final for you. That will have 2 parts to it. That will have the core piece, which is a departmental part of the final, and that's something that you'll be completing. And I have to figure out exactly how we're going to do this in terms of because it's not something I can do in Canvas as opposed, in terms of doing multiple choice or anything. It has to be, you actually have to fill in information for that piece. So I'll get back to you on that part. And then there's a second part. So that's for the first hour. The second hour will be on a typical multiple choice test that I will give, which will cover other things that were not covered in the core piece. All right, so that'll be a 2-hour test, and it will be on 2 weeks from today, I believe. All right, so we have 1 quiz left, 1 test, which is next Wednesday. So the quiz is next Monday, the test is next Wednesday, the 9th, and then the final exams the following Monday. All right, and that should complete the course. All right, so let's talk a little bit about hypothesis tests. And again, what I'm going to do is share the screen with the handout that I posted. So the question is, what is a hypothesis test? Well, the first thing, I want to compare it to confidence intervals, because what are confidence intervals? They are attempts to take our sample data and estimate a population parameter, such as a population mean. So you take your sample mean and then do something to the sample mean and convert it into an interval, and that interval will estimate the population mean. So we're going from the data and we're estimating population value. A hypothesis test is sort of the opposite. Hypothesis test is where we have a hypothesis, we have an idea, general idea about the population parameter, such as the population mean. So that's stated as what's called the null hypothesis. It's something that's accepted by most people in a particular field of study. So it's the accepted hypothesis. So it's a statement about the population mean. For example, if we wanted to know the average height of all people in the United States, then mu would be the population mean, and we would state it to be some value, maybe 67 or 68 inches, whatever it might be. All right. So we would state the null hypothesis. This is, suppose there's somebody who comes around and they're a researcher and they think that null hypothesis is incorrect. They may think one of three possibilities: that the null hypothesis is straight on incorrect, all right, which means it could either be lower or higher than the null hypothesis value, right? So that is one possibility. Another possibility is that they might believe it's greater than the null hypothesis value, or they might think it's lower than the null hypothesis value. So those are the three possibilities. Either it's different, which means it could be lower or higher. It's either higher or it's lower. So this competing hypothesis that this researcher has come up with is called the alternative hypothesis. So a hypothesis test basically has two hypotheses. It has the null hypothesis, which is sort of the accepted hypothesis. Okay, it always is expressed with an equal sign. Should always tell you that it's expressed with an equal sign. So that's how we're going to talk about it. And then the alternative hypothesis is going to be the alternative, and it will have either a greater than symbol, which means it's bigger than the null hypothesis, a less than symbol, which means it's less than the null hypothesis, or a not equal to symbol, which means it's not equal to the hypothesis. It would be greater or less than that hypothesis, the null hypothesis. So how do we write it? Well, the null hypothesis has this symbol here, H with a little 0 next to it, okay? And you can pronounce it, some people pronounce it H naught or H sub 0, one of those two. But that's how it's expressed. And if we're going to express the null hypothesis, we typically write it in symbols, and we would put a colon next to it. And if it's a population mean that we're testing, somebody's hypothesized mean, we would say something like mu is equal to 5. We'd have some number, some quantified number next to the equal sign. Okay, so and if it's a proportion, if we use p as the symbol for the population proportion of the hypothesized population proportion, you would have H naught colon, and then maybe p is equal to 0.35. Now these values I'm just picking out of the air. They're just examples, all right, of how to write these things, all right? So it's either going to be written this way or it's going to be written this way. There will be a couple of examples where we'll be looking at in the null hypothesis in terms of the difference in means or the difference in proportions, but we'll get to that on Wednesday, all right, how to write that. I just want to give you the idea that H naught is the symbol, and we always have to have a population parameter to the left of the equal sign. All right, now the alternative hypothesis, the challenging one that challenges the null hypothesis, the symbol that's used is H sub A. Okay, H sub A, we could say it like that. Right? It's H with a small a next to it. And once again, we're going to, when we write the alternative hypothesis, we'll put a colon next to it. And then we're going to have one of three possibilities. And if it's a mean, it would be mu is greater than, or mu is less than, or mu is not equal to. One of these three is going to be the alternative hypothesis. Now, if there is a number right next to the null hypothesis, it has to be the same number in the alternative hypothesis. Those two numbers have to match, be exactly the same number, right? It can't be different numbers. Same thing with proportions. If we wanted, if this was the value for the null proportion, E is equal to 0.35, then one of these three is going to be the alternative hypothesis. Now, you may ask, how do I know which of these three do we pick? I mean, which of these three do we pick as the alternative hypothesis? Well, the problem itself will tell you, all right? In most cases, it'll say the research hypothesis is going to be something bigger or something smaller. Now, typically, if there's no mention of whether the alternative hypothesis is going to be bigger or smaller than the null hypothesis, then most likely it's going to be not equal to, all right? Not equal to, which makes sense, right? I mean, if the researcher is not specifying whether the alternative value is bigger or smaller than the null value, then it's got to be something that's not equal to it. It could be either smaller or bigger. All right. So any questions so far? No questions so far. Okay. Now, in hypothesis testing, and this was brought out in the video that I posted on last Wednesday. And by the way, there was a video within the video, so just know that, with Dr. Williams. She mentioned it, and I think I mentioned it too, that initially we make the assumption that the null hypothesis is true. We make that assumption. And what we're really trying to do is we're trying to take this sample data from the one sample that we acquired. We want to take the sample data and see if there's enough evidence to say, well, this null hypothesis is not really true, that the alternative is really true. We want to see if there's enough evidence for that. So what we're really doing is if the two hypotheses are about a mean, the average, let's say average height of people, all right? And what we do is we take a look at the estimate of average height, which would be the sample height for the sample of people that we acquired, all right? We look at their sample mean. And we want to see is how far away is the sample mean from the population mean? Is it close or is it really far away? Now, the further away the sample mean is from the population mean, it would make sense that you would start to have some doubts about whether the proposed hypothesized mean, that is the null mean, in this case 5, whether that's really true or not. The sample mean is far enough away, either far in terms of being less than it or far away being greater than it, then we would start having doubts whether the population mean is really equal to 5. Okay, I hope that makes some sense. The further away the sample mean is from the population mean, the less chance there is that the population mean is really 5. So we're going to be doing something like that, but we're not going to guess at it. We're going to use a certain procedure which will tell us exactly how to come up with that answer. All right, how far away is far away, right? Because you may not be sure, but something you might inspect the sample mean and say, yeah, it looks pretty far away from the population mean. Yeah, I'm going to reject it, reject the null hypothesis. Well, you may come to that conclusion, but somebody else in the class may come to a different conclusion. So we have to have some quantitative procedure which allows us to make that determination. Is it far away enough from the null hypothesis mean? Is the sample mean far enough away? So if there is enough evidence, all right, we state that the alternative hypothesis is statistically significant. All right, what does that mean? That means that there is enough evidence to claim that the null hypothesis is probably not true and that the alternative hypothesis seems to be a better choice. Now, you can never be absolutely sure about this. That's the thing. But what we're doing is we're using a little bit of logic and a little bit of probability to come to this conclusion. Now, if there's not enough evidence, then we say there's not enough evidence to reject the null hypothesis. If there's not enough evidence, that doesn't mean that the null hypothesis is true. It just means there's not enough evidence to say it's not. Okay. And in the video, or last Wednesday's video, Dr. Williams and I also talked about the analogy of a criminal courtroom case. Suppose you're a juror in the jury, and you're there to see if somebody should be convicted of a crime. Well, if you've ever been on jury duty, you know that if it's a criminal trial, that the first thing the judge tells you is that you have to assume at first that the person is innocent. So that would be the null hypothesis. The person is innocent. And then they say, well, now you'll listen to the prosecution's case and see if there's enough evidence to allow you to go beyond a reasonable doubt and say, and reject that null hypothesis that they're innocent and conclude that the person probably did the crime. So that would be the alternative hypothesis. So again, there has to be enough evidence to make you feel as if there's a good chance that person committed the crime. So hypothesis testing is just like that. We have to gather enough statistical evidence as opposed to courtroom evidence to reject the null hypothesis. All right. So, but if we don't acquire enough evidence, if the sample data is not strong enough to reject the null hypothesis, we can't say we accept the null hypothesis as true. We cannot accept that. We do not accept that. We just say that we cannot say it's false because there's a lack of statistical evidence. Right? Hope that sort of makes sense. Now, let me show, again, this diagram here sort of explains it. Most books on statistics has something like this in their in the text about hypothesis testing. So running along the top here is something about the true value of the population parameter. In other words, it's something that's unknown. If we knew the population mean, we wouldn't have to do any testing. We would just know what it is. But since we ordinarily don't know what it is, we have to just say it's unknown. So the null hypothesis, in reality, an unknown reality, is either true or it's false, right? It just makes sense. Something's just true or something's just false. Now, what we're going to do in statistics is that we're going to take a sample and we're going to run a test, some sort of test on the sample. And we're going to determine whether there's enough evidence to reject the null hypothesis, which we call a significant result, or there's not enough evidence to reject the null hypothesis, which means it's not significant. Now, since we're running this test on a sample, not on the entire population, when we come to our conclusion, we cannot be absolutely sure that our conclusion is correct. We just hope it's correct. And therefore, there are a possibility of making an error. For example, if we run our test and the test says there's enough evidence to reject the null hypothesis, but in reality, the null hypothesis is true, so we're rejecting something that's actually true, well, that's a mistake. That's an error. And we call that a type 1 error. However, if from our sample, we find there's enough evidence to reject the null hypothesis, and the null hypothesis is false, well, that's a correct decision. On the other hand, if we do not have enough evidence to reject the null hypothesis, therefore it's not significant, and the null hypothesis is true, then we made a correct choice here, right? We didn't reject the null hypothesis, and the null hypothesis is actually true in reality. So that means the test, we did not make a mistake when we came to that conclusion. However, if we find that there's not enough evidence in the sample to reject the null hypothesis, but the null hypothesis is actually false, we've also made a mistake there. And that's a case of what's called the type 2 error. The type 2 error is when we do not reject the null hypothesis, but we should have because the null hypothesis is false. All right, so those are the two types of errors. In your textbook, and I'll show you in the textbook also, there is a little section on what's called power of the test. The only thing you have to know about this in this course is just the basic definition here. The power of the test is dealing with this box here, where we've rejected the null hypothesis and the null hypothesis is false. So the probability that we've rejected null hypothesis when it's actually false, which is a correct decision, is called the power of the test. Now, this is an important topic in more advanced statistics. Researchers who go on to graduate school and take classes in statistics, this is an important consideration. For you, the only thing that you need to know is what it is. And it's referring to this box here. It's the top row, second column, where it says reject H naught, and H naught is false. This decision right here, the probability of this happening is called the power of the test. Now, the question is, why do we define the power of the test? Is because the researcher goal is to reject the null hypothesis because they believe the null hypothesis is false. That's why they're doing the research. So since they're thinking that the null hypothesis is false, and they hope there's a very high probability that the null hypothesis is false in reality, then they want a very high probability for the power of the test. They want this to be a high probability because that's their goal. They want to reject the null hypothesis because they think it's false in reality. All right. Now, the probability of a type 1 error. This is the error where you reject the null hypothesis when the null hypothesis is actually true. That type of error is this type 1 error. The probability of it is called alpha, right? They use the Greek symbol alpha to represent the probability of a type 1 error. The probability of a type 2 error, that means when we do not reject the null hypothesis, when the null hypothesis is false, is called beta. Now, Dr. Williams in her video mentioned that, a couple different examples of alpha and beta, right? And in the book, I'll just mention to you about these two concepts that are mostly in the world of medicine. And it's something that maybe with COVID testing is brought up occasionally. And that's the idea of a false positive and a false negative. False positive, false negative. For example, false positive means if you take a COVID test, okay, and it says that you have COVID when you really don't have COVID, that's called a false positive. False negative would be is if you come back with a negative test and you actually have COVID. Now, you may be a little concerned about that if you've been tested recently because these tests aren't 100% valid. All right, no test, no medical test or laboratory test is 100% valid. So there's always a possibility there's an error that's made in when you take a COVID test or any other type of test, any other type of lab test. So false positive means it shows that you have a positive, that you got the disease when you really don't, and a false negative means it shows that you didn't get the disease when you did. Now, the type 1 error. A type 1 error says you reject a null hypothesis. That means, so it's sort of like a false positive, right? A false positive, all right? Saying if we consider the positive to be having COVID, if that's your alternative hypothesis, then the fact that we're rejecting the null and accepting the alternative that you have COVID when you really don't have COVID, The type 1 error is like a false positive, and therefore the type 2 error is like a false negative. It mentions it in the book, so I'll point that out to you. All right. Any questions about anything I've covered? Just again, a review of what we covered last time, but I do want to go over it with you guys. So alpha is the probability of a type 1 error, and it's also called the level of significance. So beta, the probability of type 2 error, is an advanced topic. Again, not covered very much in an introductory course, but we do talk about alpha. So what is alpha? Alpha, again, is the probability of type 1 error. Remember, a researcher's goal is to reject the null hypothesis. So a researcher is concerned with what? The probability that when they do reject the null hypothesis, that they're concerned that it's possible that the null hypothesis is actually true, so they made that type 1 error. So they want the type 1 error to be as small as possible. They don't want a big type 1 error. And so what researchers do up front is they select alpha, this level of significance, this probability of a type 1 error. They select it up front, and they pick some small values such as 5%, 1%, 10%, some value around that, those values there. 5% is very typical, all right? They pick that, and it's usually expressed as a decimal. Alpha's, if it's 5%, it would be expressed as alpha is equal to 0.05. So that's basically what the reason they're picking it is that they're saying basically we'll accept a 5% type 1 error. All right. In other words, 5% of the time when they reject the null hypothesis, 5% of the time they're making a mistake, which means 95% of the time they're not. Okay. So they're going to say, yeah, I accept that. That I'll accept a 5% or less level of significance. Now, that is a key part of doing hypothesis testing. By picking this alpha, and by the way, in any problem I give you, or any problem, any book, statistics book, they always give you alpha. They give you that value, all right? So don't worry about it. It's not something that you have to determine. It's given in the problem, the level of significance. All right, so it says here, when we determine whether to reject the null hypothesis or not, we're going to be using this alpha that's in the problem. We're going to use it. And I'll show you in general today how that works. And then we'll show you several examples on Wednesday in terms of how to use it. All right. So alpha is going to be selected. And using this alpha, we're going to determine if the sample statistic, or the sample that's given, is sufficiently far away from the hypothesized value of the null hypothesis to make it unlikely, this is the point, to make it unlikely that this hypothesis value is true. In other words, picture a population mean, and then you select samples from it. You're going to have some samples that will have sample means less than the hypothesized, the population mean. You'll have some samples that will have larger sample means than the population mean. And there'll be a distribution of all these possible sample means. All right. So that's called normal variation, normal sampling variation around the population mean. So we want to determine is if the sample mean that we get, if we assume the null hypothesis is true, that is the population mean is equal to some value, we're assuming it's to be true, how likely is it that we got the sample mean that we did? Is it highly unlikely or is it likely? So that's exactly what we're going to do. We're going to make that determination. And we're going to use this alpha, this level of significance, as a way of determining that. All right. So, and the last thing I mentioned also, and this we'll go into more detail on Wednesday, is the 3 types of hypothesis tests. And they correspond, by the way, to the 3 types of alternative hypotheses that we can have. We can have, again, an alternative hypothesis that has not equal to. We can have one that's less than, or we can have one that's greater than. So the alternative hypothesis determines which of these 3 types of tests that we will do. So in this handout here, I mentioned that we select our alpha up front. And by the way, there are two ways of doing the hypothesis test. And I'm just showing you one of them here. And there's a second type of way of doing it also, which I will also explain to you. And we'll go into, again, more detail on Wednesday about that. But if we have a two-tailed test, the two-tailed test says the following. The alternative hypothesis has a not equal to. So the alternative hypothesis says either you can be significantly smaller than 10 for your sample or sample mean, or you're going to be significantly bigger than the population mean. The sample mean is going to be significantly bigger. One of those two is possible for you to reject the null hypothesis. So since we're going to be using either small values or big values, depending on what the sample mean is, that we use what's called a two-tailed test. So the way to do it in this particular method is that we're going to take our alpha, which is the largest value of the type 1 error that we'll accept as a researcher. We're selecting it up front. And with a two-tailed test, we're just going to split it in half and say half of it goes to the right, half of it goes to the left. Okay. And what we do is we color in these two tails of our bell-shaped curve, okay, assuming a bell-shaped curve. And we put the mean, the proposed population mean, the hypothesized mean from the null hypothesis, we put that in the middle, because that's our mean. And we basically say, all right, I'm going to plot the sample mean that we got. Again, it could be smaller than 10, it could be bigger than 10. I'm going to plot it along this axis here. This is my x, this is my variable. And I'm going to plot it, and I'm going to see where it falls along this number line. If it falls to the right, where we have the 2.5% here, it falls to the right of this value here, it's somewhere in this region here, then we're going to reject the null hypothesis. This is called a rejection region. Or if it's smaller than 10, if it's in this, and if we plot it and it's somewhere down here, when we plot it, in this area, underneath this area here, this 2.5% area, we would also reject it. However, if our sample mean is somewhere in between these two values here, these two vertical lines here, somewhere in this area here, then this is the 95% of the area under the curve that we're not going to reject the null hypothesis. In other words, it's close enough to 10 that we're going to accept it as normal variation around the population mean. In other words, the sample mean is just normal variation. All right, not a big deal. So we're using these rejection regions as places where we say the sample mean is sufficiently far away from the population mean that we're going to reject this as the true value, because it's the probability is so small that if it's in this region here, it's such a small probability that we're going to reject the population mean as being 10. We're going to say, all right, it's not 10. In this case, it's bigger than 10. All right. Now, if the problem is about the alternative hypothesis being less than the null hypothesis value, in this case, we're looking at a population proportion being equal to 0.45, and the researcher believes that the proportion is significantly less than 0.45. Then we do what's called a left tail test, or Dr. Williams also called it a lower tail test, meaning the same thing. So if you see lower tail or left tail, means the same thing. Once again, the proposed proportion, population proportion, we put in the center of this curve. If we say, for example, our alpha, our level of significance, the largest probability that we'll accept as a type 1 error, is 0.01 or 1%. In a left tail test, we take the entire percent and put it into the left tail. All right. Remember, in the two-tailed test, we divided the alpha by 2 and put half of it to the left and half of it to the right. And that's, of course, because we're dealing with two tails. But here we're dealing with just one tail, the left tail. So we put the entire alpha to the left. We call that the rejection region, and the rest of the curve is the non-rejection region. So once again, if the sample proportion is much lower than 0.45, to the point where it's in this region down here when we plot it, then we're going to reject the null hypothesis of 0.45 and say we believe we have enough evidence to reject 0.45 as the population proportion, and we believe it's less than 0.45. At least there's enough evidence to claim that. If the sample proportion is in anywhere along the line here, outside of this rejection region, then we say there's not enough evidence to reject the null hypothesis. All right, and that's the conclusion. And finally, the right tail test would be a case where there is a greater than symbol in the alternative hypothesis. In this case, we're saying we're proposing, at least somebody's proposing population means 100, and you as the researchers thinking it's much greater than 100. And suppose alpha is 0.10 or 10%, where we believe we can accept a 10% type 1 error. Then we put the entire 10% to the right tail. It's also called an upper tail test, but we also can call it a right tail test. Put the entire 10% to the right. And once again, we look at our sample mean. The sample mean, and then, excuse me, if the population means 100, we place it in the center. And then we look at the sample mean. If the sample mean is in this, along the number line in this region here, we're going to reject the null hypothesis. If it's not, if it's somewhere down here, then we're not going to reject the null hypothesis. So what I've just showed you is what's called the rejection region method, or rejecting the null hypothesis. All right, we plot a bell-shaped curve. We plot where the alpha is. If it's a right tail test, we put it to the right. If it's a left tail test, we're going to put it to the left. If it's a two tail test, we divide alpha by 2 and put half of it to the right and half of it to the left. All right? And we call these areas rejection regions. Okay. Now, there is an alternative way of viewing all of this, and that's what I'm going to show you next. All right, I'll spend a few minutes to show you that. And then this will be over the next 10 minutes or so. I'll go over this alternative method. And then for the last 20 minutes, 18 to 20 minutes, I'm going to show you another video on for StatKey, which deals with hypothesis testing. They call it randomization hypothesis testing. We'll play that video, and then that'll be it for today. And then again, Wednesday, we'll go over quite a few examples of how to do all of this. I'll show you exactly the steps that you need to go through. All right, so it'll be quite clear to you how to do these things. All right, so let's stop sharing this screen and let's go to the book. This is chapter 22. All right, now chapter 22 is just giving an introduction to hypothesis tests. Chapter 23 also has a couple sections there on hypothesis tests. I'll just briefly mention it to you when I finish this chapter. This chapter, again, you're not responsible for the whole chapter. You're only responsible for the first couple sections in here. But I do want to bring to your attention a couple things that are mentioned in this chapter that you should look at. So again, a hypothesis test, it sort of gives you this basic definition of what it is. All right. And then it goes through some calculations. Don't mind the calculations, because the calculations would be important if you were taking a traditional statistics course, but we're not. All right, so we're going to use StatKey. So this will be a pleasant surprise for you. It'll be nice to be able to do all of this without doing using these formulas. But basically, the basic steps that are involved is, number one, reading the problem. Um, they're basically going to be short word problems that you'll be looking at. And you're going to determine, using symbols, the null hypothesis and alternative hypothesis. So number one, you're going to determine, are you dealing with a mean or with a proportion? And then you're also going to determine if there's two populations. So you might be dealing with difference in means or difference in proportions. So you're going to then write out your null hypothesis and your alternative hypothesis using symbols. Number two, it says collect data. Well, the data will be given to you. Now, is it possible that, now in this course, most likely I will give you, you'll be given the sample data, the sample mean or sample proportion, or if there's more than one population, the sample means or sample proportions. It says here, then you summarize with what's called a test statistic. Now, you're not going to do that. That's using formulas. We're not using formulas, but you're going to be doing something similar here. Number three is determine how unlikely the test statistic would be if the null hypothesis were true. Of course, that you will be doing. All right. And then you're going to be making a decision. And that decision is going to be something we'll describe more on Wednesday, but I'll mention it briefly today. All right. And I did mention it using the rejection region method using the handout a minute ago, but I'm going to show you the alternative method in a minute. All right. So once again, there's always going to be two hypotheses, the null and alternative hypothesis. All right. They give you the jury trial example, and it is an example of what a null and alternative hypothesis means. All right. Again, we've already gone over that, but you can read through that. Now here in this section, which it's supposedly not responsible for, it's not mentioned in the syllabus, but it does mention about the three types of tests: the one-sided test, which is the left tail or right tail test, or upper tail, lower tail test, and then you have your two-tail test. It does mention them here. All right, and writes it out in words, but remember, symbols are going to be used. And in the final exam, in the core piece of the final exam, they expect you to use symbols. All right, and you have to get the symbols exactly right to get credit for the problem. So it's important to. That's why I'm teaching it the symbols, so that you know exactly how to write it. All right, it's not a hard thing to do. It's just something that you have to do. All right. So they go through these calculations here. Here's test statistic. We're not doing any of these things. All the stuff that's mentioned here, we're not going to be doing. We're going to use StatKey instead. That's why I believe they decided to not consider this section important. But one thing that we're going to be talking about is this concept called a p-value, which has not been mentioned yet. So I do want to address that with you. But most of this is not, you can read through it if you like. Doesn't hurt to look at it. In this section, 22.4 is, I believe, part of the curriculum. They want you to read this, and they talk about the two types of errors, the type 1 error and type 2 error. So they do go over it here. So definitely you want to make sure that you understand it. Make sure that you understand false positive and false negative with reference to the type 1 and type 2 error. Note that the false positive is type 1 error, false negative is type 2 error, but they talk about it more in here, so you might want to read through that. And again, there's the examples here that they talk about using the courtroom example with type 1 and type 2 errors. Here are the probabilities associated with type 1 and type 2 errors. Again, type 1 errors, the probability of type 1 errors called alpha, or the level of significance. I mentioned that earlier. And type 2 errors is beta. That's the probability of a type 2 error. And then they do mention power of the test. So definitely you're responsible for that, just the definition of it. When to reject a null hypothesis. Now, in here, they talk about Now they do go through the calculations, these formulas, but they do use what's called a p-value to determine. So let's see if they have a definition of a p-value here. Look like they have it this page here. So I think what I'm going to do is hold off on the p-value unless it's in the next chapter. Actually, let me check the next chapter, chapter 23. Chapter 23 continues with hypothesis testing, but looks at it from the perspective of means. Yes, I think in 23 we do see it. So let's just take a quick look at chapter 23. Shows you the steps once again of how to do this. Now, one thing they do mention in step 3 here is determining a p-value. So again, I did not talk about that. So let me show you where that is in this chapter. So okay, again, ignore the formulas, all right, and t-tests. And here's p-values here, all right. So let me see if I can find a formal definition for it. But if it's not here, I will let you know on Wednesday about it. All right, so I do have to give you a definition of it. So most of this chapter you're not responsible for, only the first section, but I want to see if there is a formal definition, and it doesn't look like there is. Certainly do not read any of this stuff here. F-tests and t-tests and tests for slope and all, and this certainly not that. So nope, there doesn't seem to be much here on p-values. So don't worry about it. I will write it up for you, post it, all of that. I'll define it next time. All right, it's just an alternative way of doing a hypothesis test. So we'll leave that for now. Now, in the video that I will be showing you, there is a mention of p-values. So don't worry about it for now. Just listen to it, absorb what you can, and I will be again doing examples of this when we on Wednesday. So don't again bother yourself about it. All right. Okay. So let's go ahead and share. Play that video. Of course, you could play this video at any time going into StatKey. All right. And how do you get there? Let me just show you again, show you the videos. Again, getting the StatKey, hopefully you all know how to get there by now using just typing in StatKey into your browser, and then click up here for the videos. And the introductory video is on the top. And there's one called Overview of Randomization Tests. This is the one I'm going to play for you now. It takes about 18 minutes or so. Okay. All right. And one thing I forgot to do, I forgot to turn on the audio. I did remember to do that. You didn't hear anything there. So let's go ahead and do that. Should be able to hear it now.
Hi, I'm Carrie Locke Morgan, and I'm going to go through a brief introduction to randomization tests. So the motivation for a randomization test stems from the definition of a p-value, the probability of getting a statistic as extreme as the observed statistic if the null hypothesis is true. So let's break this down into two parts. So we first want to know what kinds of statistics would we get if the null hypothesis were true? And then secondly, once we have step 1 completed, how extreme is the observed statistic? So this is really the foundation for a randomization test. More formally, a randomization test consists of 2 steps. The first step is to simulate new statistics, assuming the null hypothesis is true. And then once you have these statistics, find the proportion of these simulated statistics that are as extreme as your observed statistic. I'm going to illustrate this process with 3 different examples. So the first example is Paul the Octopus, and I gave you a YouTube link if you want to watch it later. But to summarize, Paul the Octopus predicted 8 World Cup games and predicted them all correctly. So a big question in everyone's mind, is this evidence that Paul actually has psychic powers? So maybe we can't quite get at that question, but we can answer the question of how unusual would this be if he was just randomly guessing, with just a 50% chance of guessing correctly. So to put this into a more formal hypothesis testing framework, we're doing inference for a single proportion, where this proportion P is the proportion of correct guesses of all times that Paul would predict a World Cup game. Our null hypothesis is P equals 0.5 versus our alternative that P is greater than 0.5. In a randomization test, the first step is to simulate new statistics, assuming the null is true. In this case, we want to know what kinds of statistics we would observe if P equals 0.5. Well, luckily, we can simulate this just by flipping coins. In other words, we can simulate a new statistic by flipping a coin 8 times, because the sample size is 8, and recording the proportion of heads, or equivalently the proportion of correct guesses. And if we repeat this process many times, we come up with a distribution of new statistics, assuming the null hypothesis is true. Of course, if we want to repeat this many times, we're not going to sit there flipping coins over and over again. We're going to turn to technology. So there's lots of different options for technology for conducting a randomization test, and we give manuals from many of the common software packages. But for ease of illustration, here we're going to use StatKey, which is free online software that we've developed to accompany our textbook. So this is the home page for StatKey. Here we're going to be focusing entirely on this randomization hypothesis test column. Here we're doing a test for a single proportion. And our count is 8 because he got 8 correct out of a sample size of 8. So this brings in our data. We see our sample proportion of 1. Now we're going to generate one randomization sample by clicking on Generate One Sample, which is essentially just flipping a coin 8 times and counting the number of heads. So in this particular simulation, we happen to get 5 out of 8 heads, or 5 out of 8 correct guesses, for a sample proportion of 0.625, which is then plotted down here on the randomization distribution with a dot above 0.625. We can do this again, just flipping 8 coins, or flipping a coin 8 times. Here we got a sample proportion of 0.5 for 4 out of 8 correct guesses, so we see a dot appear above 0.5. We can do it again, 0.5 again, this time 0.75. You can do this repeatedly. You can start to see a distribution building up. Each time we're simulating a new statistic, assuming the null hypothesis is true. And once you get bored of generating samples one at a time, and once students start to understand what's going on, you can jump ahead and generate 1,000 samples. So now we have a distribution of statistics that we would observe if the null hypothesis were true. So now that we have this distribution, the second step in a randomization test is to find the proportion of these simulated statistics that are as extreme as your observed statistic. Or in other words, in this particular case, we want to know what proportion of these simulated statistics are as extreme as the observed proportion of p hat equals 8 over 8, or 1. So let's go back to our distribution of statistics, assuming the null is true. And we're doing an upper tail test, so we want to look at the right tail, and we want to see how extreme our observed statistic of 1 is. So we find 1 on the x-axis, and above it, in this little blue rectangle, we see that, in this case, 4 out of the 1,000 simulated statistics are as extreme as our sample proportion of 1. So what have we just done here? We've developed a distribution of the statistic, in this case a sample proportion, assuming the null is true. We then want to find on the x-axis our observed statistic, and then measure its extremity by calculating the proportion of statistics as extreme as the observed statistic. And this number is our p-value. So in this particular experiment, the probability of Paul guessing all 8 out of 8 correctly, if he really is just randomly guessing with p equals 0.5, is 0.004. And just in case you were wondering, this is very close to the theoretical value of 0.0039 that you can calculate exactly. The more randomizations you do, the more precisely you can get to this number. All right, so that's Paul the octopus, and that's our single proportion example. Now we're going to jump into an example with difference in proportions. So we're going to look at an example on cocaine addiction. So in a randomized experiment on treating cocaine addiction, 48 people were randomly assigned to take either disipramine, a new drug, or lithium, an existing drug. And our response variable is whether or not a patient relapsed. So the question of interest is disipramine significantly better than lithium at treating cocaine addiction? You may notice this is a simple difference in proportions hypothesis testing scenario. All right, so this is a randomized experiment, so just to take you through this. So we have our 48 people to be treated with either disipramine or lithium, and we randomly assign the units to the treatment groups. And this is the random process. I won't take you through all of it, but eventually they all get assigned. We conduct the experiment or give them the drug, wait and see what happens, and then observe the relapse counts in each group. So you'll notice that under the new drug, disipramine, 10 relapsed while 14 didn't relapse, and under the old drug, 18 relapsed while 6 didn't relapse. So the difference in proportions is -1/3. The crucial question is this difference more extreme than we would expect to see just by random chance? So is it plausible that just randomly more relapsers happen to be assigned to the old drug group, or is there actually something going on with the drugs? All right, so going back to our first step of a randomization test, we want to simulate new statistics, assuming the null hypothesis is true. So in this case, we want to know what kinds of statistics would be observed just by random assignment to treatment groups if the drugs are the same regarding relapses. So if neither drug causes more or less relapses. So we can do this by simulating new randomizations and just keeping relapse status unchanged. Because basically we're assuming that it doesn't matter which group you get assigned to, you're still going to relapse or not relapse, as you did in the original experiment, because we're assuming the null hypothesis is true. We want to see what would happen just by the random allocation to treatment groups. So we have our data, we pool everyone back together, and we re-randomize or simulate another randomization. This, by the way, is why it's called a randomization test, because we're simulating randomizations most often. And as we're doing this, we're keeping the relapse status fixed because we're assuming the null hypothesis is true. So in this particular randomization, the new drug had 16 relapses, while the old drug had 12 relapses, for a difference in proportions of 0.167. We can do this again if you want, and we get a difference in proportions of 0.25. So ideally, we'd like to repeat this process many, many, many times to really get an idea for whether our observed difference in sample proportions is actually extreme. So we're again going to turn to StatKey, and now we're doing a test for difference in proportions. So in original data, we had 10 out of 24 relapsing under the new drug and 18 out of 24 relapsing under the old drug. And we see our difference in proportions of -1/3. So if I click Generate One Sample now, I'm going to reassign the units to treatment groups, keeping the relapse status the same as we just did in the PowerPoint slides. So I'm simulating statistics that I would get just by random chance or just by the random division into treatment groups if there really is no differences between the drugs or if the null hypothesis really is true. So in this particular randomization sample, we got a difference in proportions of -0.25, which is plotted with a dot here on the randomization distribution. And we can do this again and again, building up randomization statistics or simulating new statistics, assuming the null is true. And we can go ahead and generate 1,000 samples, or even if we want to, maybe a couple more and get up to 4,000 or 5,000 samples. The more samples you generate, the more accurate your p-value will actually be. So now we have a distribution of statistics, assuming the null hypothesis is true. And the next step is to see how extreme our observed statistic of -1/3 actually is. So in this case, we're doing a lower tail test. We want to look at the left tail because we want to see if the proportion of relapses under desipramine is less than the proportion of relapses under lithium. So we're looking at finding -0.333, our observed statistic, on the x-axis, and calculating the probability in the tail. So in this case, we see the proportion of simulated statistics as extreme as our observed statistic, or in other words, the p-value is 0.019. So it looks like there is some significant evidence that desipramine is better than lithium. So just to take you through this again, we have our distribution of the statistic, assuming the null is true. We find our observed statistic on the x-axis and calculate the proportion as extreme as the observed statistic. Or in other words, we find that the probability of getting results as extreme or more extreme than those observed, if the null hypothesis is true, is about 0.02, which in this case is the p-value. All right, so that's our second example. We've done a proportion, we've done a difference in proportions. Now we're going to turn to a difference in means. So we're going to look at sleep or caffeine for memory. So this is based on an experiment in which students were given words to memorize and then randomly assigned to either take a 90-minute nap or to stay awake and take a caffeine pill. 2.5 hours later, all students were tested on their recall ability. And the question we want to answer is either sleep or caffeine better for memory? So in this case, our parameters of interest are the mean number of words recalled if a student either sleeps or consumes caffeine. Our null is that the two means are equal or that there is no difference in means. And our alternative is that the two means are not equal or that there is a difference in means. All right, so here's our data. The sleep mean turns out to be 15.25. The caffeine mean turns out to be 12.25 for a difference in means of 3. Big question, is sleep actually better than caffeine for memory, or did the people with better memory just happen to get randomly assigned to sleep? So to answer this, we need to actually do a randomization test. We need to simulate what would happen just by random chance. So again, here's our data. What we want to know is what kind of results would you see just by random chance if there were no difference between sleep and caffeine. So just like we did with the cocaine addiction problem, we're going to basically reassign all the response values to different treatment groups. Or we're going to see what would happen just by the random assignment to either sleep or caffeine if whether they sleep or have caffeine has no effect on the number of words recalled. So we're going to keep the response values unchanged and randomly reassign people to either sleep or caffeine. This is, again, to simulate statistics that we would get if the null hypothesis were true, or if there is no difference between sleep and caffeine for memory. In this particular randomization, our sleep mean is 14.25, our caffeine mean is 13.25, so we have a difference in means of 1. Ideally, we'd like to do this many times, so again, we're going to turn to technology. So we're going to go to a test for difference in means. I'm going to bring up the sleep caffeine words data. So here you can see the data, the original data that we were looking at with the difference in sample means of 3. So if I click now generate one sample, I'm randomly reallocating each value to either the sleep or the caffeine group to see what would happen just by random chance or just by the random assignment to treatment groups if there is no difference between sleep and caffeine for memory. So in this particular randomization sample, we got a statistic or a difference in means of negative 1.67, which is plotted down here on the randomization distribution. Could do this a couple more times, speed it up, and we can generate 1,000 samples. So now we have a distribution of the statistic, or in this case, the difference in means, assuming the null is true. Again, we want to see how extreme our observed statistic is. So in this case, we have a two-sided alternative. So we're going to look at both tails, and we want to see how extreme our difference in means is of 3. It actually already came up right here. So we're looking at our observed statistic of 3, and we see that on either side, about 0.025 of the values are as extreme as 3. We have a distribution of the statistic, assuming the null is true. We find our observed statistic on the x-axis, and we look at the proportion as extreme as that. It's going to vary, values are going to vary a little bit from simulation to simulation. Here we have 0.024, whereas in the simulation I showed you, we have 0.025. But that's okay. If you're worried about that, you can just generate more randomization samples to get a more precise estimate. In this case, we're looking at both tails. So the p-value is the proportion as extreme as the observed statistic, which is the proportion in both tails, or in this case, 0.048. All right, so you now know how to conduct a randomization test. First step, simulate new statistics, assuming the null hypothesis is true. Second step, find the proportion of these simulated statistics that are as extreme as your observed statistic. And the nice thing about a randomization test, besides the fact that it helps students intuitively understand the definition of a p-value, is that it's always the same process, no matter what you're testing. So there's not a whole long list of different formulas to learn. It's really just these 2 steps. All right, thanks for listening. And additional information can be found at our website, www.lock5stat.com.
Okay, any questions about that? Now, I'll show you on Wednesday how to use StatKey to come up with something similar to what she was saying. And I'll define that p-value thing a little more precisely so that you understand what it means. And we'll take it from there, all right? So this was just an introduction to it. And then we'll actually do some problems, several of them, using StatKey on Wednesday. Any questions? Okay. All right, so I'll stop the recording.